Hi, my name is Hiro Ali, and I will be presenting the environmental cooling systems of the Piper PA 44180 Seminole. The environmental cooling system is a very important component to all aircrafts. Understanding the basic components of the environmental cooling system may even save your life in some occasions. In this presentation, I will explain the components of the system and why it is important. I'll also explain the pre-flight requirements for it and go over a brief history of the environmental cooling system. So starting off with the Piper Seminole's cooling system and its functions. In the Piper PA Seminole, when the heat is not desired, you can place the switch in the fan position, and the ventilation from the fan will blow fresh air through the heater duct for the cabin ventilation and windshield defogging. To let fresh unheated air in during flight, make sure the air intake is open and the heater is off. Ram air enters the system through ducts and can be individually regulated at each outlet on the floor. There's also overhead outlets which supply fresh air for cabin ventilation. The passengers for each seat can manually adjust the outlet of the ceiling to regulate the flow of fresh air to that seat that they're sitting in. There's also a fresh air blower that is installed during ground operation. Operation of the fresh air blower is also controlled by the three-position switch that is located right next to the cabin heat switch. The fans then circulate the air with the filtered air throughout the cabin, based on how you want it. A brief history of it. The first cooling system was developed by the Wright brothers in 1902. It was consisted of a radiator which was installed above the airframe, a hose which connected the radiator or to the crankcase, and just a water jacket around the cylinders of the motor. The radiator was placed high above because the brothers used gravity to feed the coolant water into the engine. The water is circulated around the engine and picks up heat from the cylinders. Then the water returns to the radiator through the two return hoses, and then during flight, airflow through the vanes of the radiator, and the heat is turned into air and is carried away from the aircraft. That's how the cooling system for the Wright brothers functioned. Oops. But today we have advanced so much farther in technology and made more superior cooling systems due to all the knowledge we gathered. We learned from the mistakes of the Wright brothers that they had flaws in their creation and they weren't perfect. The Wright brothers only cooled the cylinder which made the combustion chamber hot. We learned and manufactured now and have ways to cool the combustion chamber as well. Now for the pre-flight for the cooling system. Pre-flighting the cooling system consists of a visual inspection of the compressor, drive belt, pulley system, hoses, condenser inlet, and condensation outlet drain. First, you have to see if the system is operable, so you look for damage or any obvious signs of system failures. When you turn the systems on, make sure it operates with 1 to 2 minutes, otherwise shut it down. Next, we have two types of air cooling units, air cycle machine and the vapor cycle system. The ACM bleeds compressed air from the turbine engine and allows it to expand, causing cooling. ACM is used in large aircrafts. In vapor cycle systems, a pressurized liquid refrigerant evaporates, causing a temperature reduction. How these function and the components and all. The cooling system is divided into two parts, and there is a high pressure side and a low pressure side. The high side begins at the compressor discharge of high pressure refrigerant vapor, driven by the engine throughout a belt and a pulley system. Then the refrigerant passes through copper coils surrounded by cooling fins to maximize refrigerant heat transfer to outside air. After leaving the condenser, the liquid refrigerant goes to the receiver or dryer. The receiver or dryer then functions like a system's reservoir, basically. Next is the thermal evaporation valve. This valve basically meters the refrigerant and maintains high pressure upstream. As the liquid leaves the valve, it is sprayed through the coils, expanding as it goes, assuring complete evaporation of the liquid by the ends of the coils. This is where the low pressure side begins. With the refrigerant turning into low pressure liquid, it is efficiently low pressure, equivalent to the condenser unit, and it consists of parallel circuits of copper tubings with fins. As a hot air in the cabin passes around the evaporator fins, its heat transfers to the refrigerant and continues into the cabin as cool air. This heat raises the refrigerant temperature to boiling, causing it to change state from liquid to vapor. One indication of insufficient freon is little to no cooling air and a buildup of frost on the evaporator. A hissing sound in the evaporator is yet another indication that there's a problem in there. Completing the system, the liquid freon now goes back to the compressor and begins the process again. These are the sources that I used to make this presentation. If you have any comments or concerns, please comment below and I'll gladly respond.